What will happen to the Earth, the solar system, and the rest of the universe as time goes by? What does the future of the universe hold? Don't panic, but our planet is doomed. It's just going to take a while. Roughly 6 billion years from now, the Earth will probably be vaporized when the dying sun expands into a red giant and engulfs our planet. But the Earth is just one planet in the solar system, and the Sun is just one of hundreds of billions of stars in the galaxy. And there are hundreds of billions of galaxies in the observable universe. What is in store for all of that? How does the universe end? The science is much less settled on how that will happen. We are not even sure if the universe will come to a firm final end or just slowly tail off. Our best understanding of physics suggests that there are several options for the universal apocalypse. It also offers some hints on how we might just maybe survive it. But of course, our capacity to predict the future of the universe is limited by how much of it we can observe. Well, let's get straight to the point. In this video, we will present the concept of the future of the universe in physics. So, let's get started. The future of the universe. What is the possibilities of upcoming universe? There are three possibilities in terms of physics. The first one is average density, known as ρ, of the universe is smaller than critical density, which is ρc. The second is average density of the universe is greater than critical density. And thirdly, average density of the universe is equal to critical density. But what does these possibilities mean?
The first possibility of our future universe is when the average density ρ is smaller than ρc, the critical density. In this case, the universe is considered open. The expansion of the universe will never stop. New galaxies and stars cease to form, and existing galaxies and stars will end up. For example, backdrafts, neutron stars, and black holes. Our future universe will become an icy death. The second possibility is when ρ greater than ρc. That means the average density of the universe ρ is greater than the critical density ρc. The universe is closed in this case. The expansion of the gravity will stop sooner. The universe will begin to contract. Progression of events will be reversed after Big Bang, and another Big Bang may occur. If so, the universe is cyclic, no end and no beginning. The third possibility is ρ equal to ρc. In this case, the average density of the universe ρ is exactly equal to the critical density ρc. The universe in this case is said to be flat, and the rate of expansion of the universe will ever decrease, but the universe will not contract. And here is the three cosmological model. Here we can see when ρc is greater than ρ, the space is negatively curved. A two-dimensional analogy is a settle. In other case, when ρ greater than ρc, the space is positively curved. A two-dimensional analogy is the surface of a sphere. However, in all cases, space-time is curved. Here are some diagrams of two-dimensional analogies of the geometry of space. Here is derivation of critical density ρc. We take E equals to KE plus U. Kinetic energy is equal to negative potential energy, while kinetic energy is equal to half mv squared, and potential energy is equal to negative gmm per r squared. And the volume of universe V equals to 4/3 pi r cubed. And the density of universe ρc is equal to mass per volume. According to Hubble's law, V is equal to HR, while H is the Hubble's parameter. And from equation 1, 2, 3, and 4, we can get that ρc is equal to 3h squared divided by 8 pi g. The value of rho c is equals to 8.9 times 10 to the power of negative kg per meter cube. This is just a reasonable value of rho c because the Hubble's parameter is not accurately known, and the reasonable value of h is equals to 21 km per second per million light years.
So let me continue about dark matter. In dark matter, we learn about luminous matter is not the only matter in the universe. The actual density of the luminous matter in the universe is just a few percent of critical density. Adding in the mass equivalent of the radiation in the universe increases the density only a little. Large amount of dark matter is also present. At least 90% of all matter in the universe is non-luminous. For instance, the rotation speed of the outer stars in spiral galaxy are unexpectedly high, which suggests that a spherical halo of invisible matter must surround each galaxy. Still, other observations support the idea of a preponderance of dark matter in the universe. Next, we learn about what can the dark matter be. They have three. First is about ordinary matter, too small to support fusion reaction that will make them star, dwarf stars, and also black holes. Next is neutrinos. Sea of neutrinos have little mass and pervade space. And for cold dark matter, two main kind of cold dark matter, which is WIMPs and Axion. So what are they? So for WIMPs, weakly interacting massive particle, which is hypothetical leftover from the earlier moment of the universe, such as Potino, one of the particle predicted by the supersymmetry approach to elementary particle. So for Axion, weakly interacting boson, which is associated with a field introduced to solve a major difficulty in the standard model. Both of WIMP and Axions are being sought experimentally, thus far without success. Next, we going to the inflationary universe. So this inflationary universe proposed by Alan Guth after the Big Bang. So the inflationary universe automatically take care of a number of previously troublesome problems in the Big Bang picture. The universe underwent an extremely rapid expansion triggered by the separation of the single unified interaction into the strong and electroweak interaction. And Guth also conclude that the density of matter in the universe must be exactly the critical density. So you can see the graph. So what we can conclude based on the graph is the dark matter needed to account for the motion of star in galaxy and of galaxy in galactic cluster bring the total density of the universe up to 0.1 critical density. Next, if the inflation scenario is correct, then the universe is not only perfect flat, but as much as perhaps 99%, not merely 90% of the matter, it is dark matter. So I will pass it to Isyraf. Thank you.
As a conclusion, these predictions are actually pretty solid and logically make sense as the likely outcome. But although these explanations are hardly what we would call concrete, they are the best explanation we have at this point in time by what all the scientists have used and researched. Who knows? Maybe we will have to actually wait for the event to occur to be sure. We came to the conclusion that this information is not 100% reliable. Perhaps for the predictions to be reliable, there will seem some information along the lines of actual evidence that the events leading up to these predictions occur. This prediction may be hard to come by without waiting till the actual event occur. If you feel let down by this gloomy conclusion to all things, take solace in knowing that this outcome is only the future as it might be. Until we understand the true nature of dark energy, the fate of the cosmos will remain mystery. The universe might yet have a surprise. So that's all from us. Thank you and bye.